This conference will now be recorded.
Hello students, welcome to the PYQ discussions on JEE Mains advanced papers. Today I have picked up numerical problems from JEE Mains paper 2021 that happened on 26th August shift 1. So today we will be discussing only the questions asked from the 11th portion. So let us start our discussions. So this is the first problem. You can see this problem is from KTG, kinetic theory of gas. The question says the RMS speed of the molecules of hydrogen, oxygen, carbon dioxide at the same temperature are VH, VO and VC respectively. Then which of these four relations will be correct? Which one will be correct out of these four? So VH, VO and VC, these are RMS speed of hydrogen molecule, oxygen molecule and carbon dioxide molecule. Look students, here we need to remember the formula for RMS speed. So RMS speed is given by Vrms square root of 3RT by molecular mass. Okay, so this is the formula. So we can see that Vrms is inversely proportional to the square root of molecular mass, right? So in this case, look, molecular mass of hydrogen will be nearly 2, molecular mass of oxygen will be nearly 32, and for CO2 it is 44. So according to this relationship or this variation of Vrms with the molecular mass, hydrogen will be having the greatest speed because it has smallest molecular mass. Okay, then the RMS speed of oxygen will be there, and then the least RMS speed will be for the carbon dioxide. Okay, look, then VH greater than VO greater than VC. So this option will be correct for this question. Okay, so option B will be the correct answer for this. Excuse me. So this was very simple. If you can remember this particular formula, or see here you have not been asked to find out the exact value. In general, there will be no questions asking you the exact value of Vrms. So if you can remember Vrms proportional to square root of T by molecular mass, this is also fine if you can remember, but you have to remember this formula to solve this kind of problem. Okay, we'll move on to the next problem. So next problem is this one. So this is actually from measuring instrument. See, in a screw gauge, fifth division of the circular scale coincides with the reference line when the ratchet is closed. Let me show you the screw gauge here. See, this is the ratchet. Okay, this is ratchet R. You can see that this is the ratchet. So these are actually spindles or starred screw, you can say starred and screw. So when this is closed, that means, the stud and spindle touch each other. At that situation, see, this is the reference line or baseline of main scale. This is the baseline. This is called reference line as well. And this is the circular scale. You can see this along this way. Okay, this is the circular scale. Now, according to this problem, see, the baseline of the main scale coincides. See, zero line is somewhere down here, and it is actually matching with the fifth division. Okay, that is what it is said. Okay, so suppose this is fifth one. Okay, here things are there. So 1 2 3 4, one more. Let me draw it clearly. So this is your screw head where there is the scale. Okay, so suppose your zero line is here somewhere. 0 1 2 3 4 5, kind of that. Yeah, okay, so 1 2 3 4 5. So this is matching with the reference line. That means, your zero line is below the baseline. So what is this indicating? Actually, the first line is saying about the error. In a screw gauge, fifth division of the circular scale coincides with the reference line when the ratchet is closed. So this is indicating your error in this instrument. Okay, so we have got error. This is called zero error. So what is zero error here? The value we have got 5 circular in circular scale. So 5 divisions, and whether it is positive or negative, how do you understand? If this zero line is below this baseline, then it is positive. If this was here, zero line was above the baseline, then it will be negative. So in this case, you have got the zero error, 5 divisions. Okay, 5 divisions with positive value. Okay, this is divisions actually. 5 divisions. You don't get the value till now in terms of main scale. Now the question further says there are 50 divisions on the circular scale. So there are 50 divisions on the circular scale, and the main scale moves by 0.5 millimeter on a complete rotation. That means you have got screw pitch as 0.5. You have number of divisions, total number of divisions on the circular scale, that is 50. So what you get as least count. Least count is pitch by the number of division, that is 50. So you will get here, this is in millimeter, right? This is millimeter, so you'll get this as 0.01 millimeter. Okay, so you have got least count. Now this is saying about particular measurement. Okay, or particular observation. For a particular observation, the threading on the main scale is 5 millimeter. That means the main scale you have up to here. Okay, this is 5. Suppose 5 millimeter, up to 5 millimeter. It is seen on the main scale, and circular division is 20th division of the circular scale coincides with the reference line or baseline. So calculate the true reading. So true reading will be actually true reading R is equal to the main scale reading. I'll write MSR main scale reading plus circular division or circular reading CSR, circular scale reading, into the list count. Okay, along with that there will be either plus or minus zero error into the list count. So this is actually the total reading. That means you have to get the main scale reading, that is 5 here, 5 millimeter. Okay, 5 millimeter. So circular scale reading is 20, list constant is 0.01. This is also in millimeter. And here see, when I have got positive error, you have to actually subtract the error. So this is 5 into list constant, sorry, list count, that is 0.01. Okay, so you look, this is 5.2 minus 0.05. So this will be in millimeter. So this will give you 5.15 millimeter. Okay, mm. Here option B will be the correct answer for this question. So dear students, I hope you have understood. So how the zero errors are added and subtracted. When positive error is there, then you have to subtract from the reading. Okay, total reading MSR plus CSR into LC. So from there you have to subtract the value of the zero error. If your zero error is positive, negative, I would have added with that. Okay, so positive error has to be subtracted and negative error has to be added. Okay, with the reading. So this is how you have to solve. So you have to remember the terms: baseline, what is circular scale reading, what is main scale reading. Okay, so these are the things you should keep in mind. All right, we'll go for the next problem. So this problem is very interesting, and look, this question says two narrow bores of diameter 5 mm and 8 mm are joined together to form a U-shaped tube. Let me try to draw it. Kind of this. Okay, so see, two narrow bores, one diameter 5 and another has diameter 8, like this. Okay, this is for 5 and this is having, you just take this as a representative figure. This is not very artistic. Okay, so you can understand that this is having greater radius. Let us say this is R2 and this is R1. Okay, so this is a YouTube now. So okay, so now if this YouTube contains water, what is the difference in the level of two limbs of the tube? That means, you know, if you pour water here, so what will be the height difference? Okay, or level difference in the level. So look here, suppose this will be level here. Okay, and here it will be like this maybe. So you might be thinking, why do I have level difference at all? Okay, why do we have level difference? Okay, let us consider 2 points over here or maybe somewhere here, A and B here. So these are at the same horizontal level, okay, while inside the liquid or water here. So these two guys will have actually same pressure, right? These two guys will have same pressure at these two because they are at the same horizontal level. Let us say this height is h and this height is delta h. Okay, that means you can see that the water level, see here there are few more informations given. See, the surface tension of the water is given 7.3 into 10 to the power minus 2 meter Newton per meter. Angle of contact will be 0 and G is given as 10 meter per second square. Density of the water is 1000 kg per meter cube. These are the things given. Look, if you remember, in case of capillary action, so if you have a narrow bore tube and you dip in a liquid of surface tension T, then the height, okay, a rise of liquid inside the capillary will be given by H is equal to 2t by 2t cos theta divided by 2t cos theta divided by rho r and g, where r is the radius of the capillary, right? Now we can solve this problem directly. Let me directly solve with this using this formula, and then I'll tell you in detail how it is true. Okay, why there should be any pressure difference at all. I'll tell you that. One reason is this one. You can see that. See, uh, this one, because so as this r is different for both the capillary, so the height rise will be different. Otherwise, see, otherwise if there was no difference in the radii of the capillary tube on both arm, then the level would have been same because of atmospheric pressure at the open end. Okay, but here the pressures will be different. Okay, pressures will be different. That's why this will be depressed, or the level will be little lesser than the level in the left arm or the narrower arm. Okay, so as you can understand from here, because the height, see, height is capillary rise is inversely proportional to the radius, right? So look here, I can just find out, see, h1 is equal to 2, see, cos theta, theta is the angle of contact, so theta is 0 over here. I can write h1 is 2 2t divided by rho g r1. Similarly, I can write h2 is equal to 2t divided by rho g and r2, right? Now I can just get the difference. Okay, get the difference delta h from here. See, 2t by rho g, these are common, so I can find. So diameters are given. Let us just multiply 2 numerator and in the denominator both places, so I can use the diameter directly. So I can write 4t here by rho g. Okay, and here I have got diameter. So diameter is 5 millimeter. That means 10 to the power minus 3. Sorry, 10 to the power 3 will be here, and here also there will be 10 to the power 3 divided by 8. So basically, what I am getting here, delta H is equal to 4t divided by this into 10 to the power 3 here. Okay, and see, this you have to do this LCM. So this will give you 3 by 40. You can see that. So 8 minus 5, and in the denominator there will be 40. So I'll get, okay, let me just go ahead with another line. 40 into 10 to the power 3 divided by rho into g into 3 by 40. So this 4 will cancel with this. So I'll get here, see, this T into 3. See, rho is how much? 1000, right? 10 to the power 3. G is 10. So I'll get here, I'll write down this rho and G here. Rho is 10 to the power 3. G is 10. So 10 to the power 4 and this is 1. So 10 to the power 5. So I'll multiply 10 to the power minus 5 in the numerator. Okay. So finally I get 10 to the power minus 5 here. So I get 3t. T is, so 3 into 3 point, sorry, 7.3 into 10 to the power minus 2, then here 10 to the power 3, then 10 to the power minus 5 again. Okay, so what you get? 10 to the power 3, 10 to the power 5, 10 to the power minus 5. Okay, fine. So here I get, okay, so this much, and see, I get 10 to the power 10 to the power minus 4. Okay, 10 to the power minus 4. So I can make this in meter. So I can make 2.19 into 10 to the power minus 3 meter, which is 2.19 millimeter. So the first option will be the correct answer for this question. Okay. So I think this become a little bit messy here, but anyway, you can understand the way I have done. Now, this I have done just from the formula. If you remember, that is very good. If you don't remember also, you can derive it, but that will take little longer time. For the sake of your understanding, let me just do that, how we can understand that this is correct, okay, or why this level difference is at all coming. As I said, it is because of the capillary rise. Amount of rise will be different in different capillary because of their boring. Boring is actually having different radius, right? So this is not required. I'm just removing this. Just let me clean this whole board except this figure. Okay, so look here. So when I have a bubble, see, a bubble, water bubble, so there will be some pressure outside, some pressure inside. Okay, all right. So to have this spherical shape of the liquid drop, there should be some excess pressure inside. So what is that excess pressure? So excess pressure is actually given by 2T by R. Okay, this is the excess pressure 2T by R. See, this I can write as P excess. Okay, P excess pressure. Look here, there are, see, bubbles forming here. If I just draw this is with radius R1, this is with radius R2, right? So there will be pressure. See, atmospheric pressure will be there, and also there will be excess pressure, like pressure inside the bubble. So actually, this pressure will be not exactly the atmospheric pressure. If there was no capillary rise and all, the pressure should be same, that is atmospheric pressure on the both arms. Okay, but here, see, these tubes are very narrow, so there will be capillary rise because of this excess pressure. So atmospheric pressure minus, so here what will be the pressure actually? Let us say this is pressure P1 here, and here it is P2. After, see, P1 is what? I can write P1 is equal to, see, the atmospheric pressure that is coming acting downward. Okay, so that is this minus the excess pressure 2T divided by R1. Okay, similarly P2 will be P atmosphere minus 2T by R2. So these are the pressures actually, except, see, since these two are different, see this one, these excess pressures are different in different arms. That's why there will be different pressures, and that's why there will be level difference also. Okay, now if I take these 2 points horizontally, they are situating, that means their pressure should be same. PA must be equal to PB because they are at the same horizontal level, right? So then what is the pressure here? See, I have taken, this is H. Okay, this height is H. So at here I'll get the P1 pressure plus H plus delta H into rho G at P1. Okay, what will be the pressure at PB? PB pressure will be P2 plus H, rho and G. Now I'll just go to the next page and show you. See, P1 plus H plus delta H rho G is equal to P2 plus H rho G. Now I have to find out delta H, so I'll keep this delta H rho G. See here, P2 minus P1 and H rho G minus H rho G, they will actually cancel each other, right? So here I have got P2. P2 I know, atmospheric pressure minus 2T by R2, and this is P1, we know, minus atmospheric pressure minus or minus plus 2T by R2, sorry, R1. Okay, look, this atmospheric pressures, they will be cancelling each other. So what we get? 2T by R1 minus 2T by R2. So delta H is actually becoming 2T by rho G whole into 1 by R1 minus 1 by R2. This is what I had done earlier also, directly from the concept of, say, this one, H is equal to, if you know the formula, you can go for that, 2T cos of theta divided by rho R and G. From this formula I have got the difference there. Okay, level difference. So I have got the same formula here also. Okay, like same thing I have got. So if you put the value of T, and this actually, this will give you 2.19. I'm not doing further millimeter. Okay, so dear students, I hope you have understood. I have solved this in two ways. One, just directly, in one method I have directly solved it using the formula of capillary rise, and in second case I have derived this level difference, okay, from the concept of pressure, okay, at the same. So I hope you can grasp it. I hope you can grasp it if you see the video carefully and write it down in your notebook. So we'll move on to the next problem. Okay, so this problem says the initial mass of a rocket is 1000 kg. So this is from conservation of linear momentum. This is a problem from conservation of linear momentum. The initial mass of a rocket is 1000 kg. Calculate at what rate the fuel should be burnt so that the rocket is given an acceleration. That means, okay, so you have to see rocket should be given this much acceleration anyway. So the question is, what should be the rate of burnt? Okay, rate. What should be the burnt? What rate the fuel should be burnt? Okay, so that the rocket will be given 20 meter per second square acceleration. The gases come out at a relative speed of this much. Okay, 500 meter per second with respect to the rocket. So look, I'll just draw the free body diagram. Suppose this is a kind of rocket, so there will be narrow hole over here and the gas will be coming out with very high speed and give a downward thrust to the atmosphere. See, there will be fuel over here. Okay, fuel. This is the nozzle, narrow nozzle through which the gas produced after burning the fuel will come out through this narrow nozzle. It will give a very high thrust to the atmosphere, and atmosphere in turn will give up thrust. Okay, so look here, the change in the linear momentum F into T, or the thrust, up thrust given in the upward direction is Ft, and see the mass, sorry, the weight of the rocket will be acting downward, and the resultant of this will actually give you the force up thrust. Okay, up thrust. Okay, and see here also you have to actually remember few formula to solve this problem accurately within time. So up thrust, or the force of thrust in the upward direction, is given by the rate of change of the mass of the fuel into the relative velocity of the gas coming out. Okay, see this is actually the rate of change of the mass. This is what we have been asked to find out. Okay, so relative velocity is given. See, this one is 500 meter per second, and see the acceleration is given. See, rocket has initial mass 1000. Okay, so we can actually take this acceleration, this mass, and see what we can do. We can actually get dm dt from here. Dm dt is equal to F thrust divided by V relative. Okay, I'm sorry, there will be actually, just a minute. I'm sorry, this is actually F thrust. This is up thrust, okay? Up thrust is this one, okay? Up thrust is this one. So up thrust minus mg. Yeah, this will actually give you m into a. Okay. So from here I have to actually find out this dm dt. So dm dt into v relative minus mg is equal to ma. Okay. So this one I know. I have to find out this one. Let me use this space here. So dm dt into relative velocity is 500 meter per second, and then you have m into g, that is 1000 kg. I am taking initially 1000 kg, m into g is again 10. This is equal to ma, the thrust given. See, the thrust is m into a is actually 10 10 sorry 20 meter per second square, and m is 1000 kg again here. 1000 kg and 10 to the power, sorry, only 10, not 10 to the power, only 10. So from here actually we can find out the dm dt. So how can you find out that? This is 20, so 2. Look, dm dt into 500, and here it is 20,000 minus plus, so this is, yeah, so it will be actually 20 plus 10, so 30,000. So dm dt will be divided by, so 30,000 divided by 500. Okay, so you get 60 kg per second. Okay, this is the answer. Okay, 60 kg per second. So option D will be the correct answer for this question. Okay, now let us go to the next problem. Okay, so this is also a very interesting problem. The problem says a soap bubble of radius 3 centimeter is formed inside another soap bubble of radius 6 centimeter. That means, let us say this is 3 centimeter, and this is formed inside another bubble. Okay, another bubble which has radius 6 centimeter. The radius of an equivalent soap bubble. Okay, if I just take this as a single one, okay, single one, so maybe this will be a little bigger. We don't know what will be that. Okay, so this is supposed R equivalent radius. Okay, we have to find out actually the radius of an equivalent soap bubble which has the same excess pressure as inside the smaller bubble with respect to the atmospheric pressure is dash centimeter. So here, what will be the excess pressure in this small soap bubble? See, it has its its own curvature. Due to that, there will be excess pressure. So that is given by, since the same material there was, so there is no mention of whether it is, okay, this is soap bubble, right? Soap bubble will be 4s by 4s, s is the surface tension by r. So this is for its own, so r1. And when you have another bubble outside, so due to that also there will be another excess pressure that will be added to this. Okay, so 4s by r2. So the total total excess pressure for the smaller bubble will be added up. Okay, the excess pressure in the smaller bubble will be delta P, suppose, and that is given by 4s by r1 because of its own curvature and because of the bigger one, that is 4s by r2. So I get 4s by r1 is 3 centimeter. Okay, I'm just keeping in centimeter, and this is 4s by 6 centimeter. Okay, so it will give you 4s 1/3, this is 6, so 2 plus 1 by 6, so this will give you actually 3, so 4s by 3. Okay, we have delta P 4s by 3. I hope this calculation was okay. So 4s by 3 is the excess pressure. Now I have got equivalent bubble which has radius this, so I'll get, since it is a soap bubble, this I'll get like this itself. Okay, and this is, so this is the excess pressure that will be equal to delta P, which is nothing but 4s by 3. So what will be this? 4s I can cancel out. Okay, let me just check once again. Four s, I don't know what was this, 3 by 6. Oh, I see, this will be 2 actually, this will be 2 here, there was mistake anyway. So this is 2, 4s I can cancel out, so R equivalent will be actually 2 centimeter. Okay, R equivalent will be 2 centimeter. All right, so here it will be 2 centimeter. So we'll move on to the next problem. So guys, I hope you have understood this. So why this small bubble is having additional pressure, because of the outer layer also. See, whenever there is a curvature, see, if you have a flat surface like this, then you have equal pressure from both sides. So that's why it is actually flat. But if there is like there is kind of this curve, so the pressure will, there will be some excess pressure along the, like inside this, or along the, or towards the concave surface. Okay, always say my surface is bubble, surface is this, then there will be excess pressure in the concave surface. Always there will be some excess pressure inside the concave surface. So so pressure will be there due to this bigger one, due to the smaller one of its own. Okay, so that's why this pressures will be added to that, so that that excess pressure will be equal to the excess pressure of this equivalent one. That is what we have done here. Okay, so I hope this is clear to you. Now we'll move on to the next problem. So second, okay, so let us solve this problem. This problem says So this problem says a uniform chain of length 3 meters and mass 3 kg overhangs a smooth table with 2 meter lying on the table. So let me draw the chain. Okay, so suppose there is, okay, so this is a chain. Okay, so this is 2 meter here and this is 1 meter over here. Okay, lying on the table 2 meter and hanging 1 meter. This is smooth one. Okay, if K is the kinetic energy of the chain in joule as it completely slips off the table, then the value of the K. Let me draw another figure. See, since it is a smooth one, as you keep like this, so this chain will actually slips down, and suppose the whole chain is at certain point, it is like this. Okay, and this has got the whole length 3 meter. Okay, 3 meter. The whole length is 3 meter, so it is slips. It has slips down like this. Okay, from the table, surface of the table. So this was initially there when the chain was not having any motion. Okay, so this problem can be solved using or applying conservation of energy. Okay, conservation of energy. So look here, when it was not in motion, so kinetic energy, initial kinetic energy is 0, but there was certain potential energy. If I say this is a reference level potential energy, so potential energy for this much length will be, see, I have total energy, initial energy, let us say EI, so that I have to write KI plus UI is the potential energy, right? So Ki, as I said, it is 0 because it was not in motion. And see, if I just think this as the reference level, so the potential energy will be negative because the length is, or the height is in the downward direction with respect to the reference level. So I'm taking negative potential energy, and see how I get M, G and H. See how much is the length hanging here. This is 1 meter. So what will be the height? You might be writing it 1 meter. But what is M and M? M, you should take the mass of this 1 meter length alone. Okay. But where that mass will be situated, that will be approximately at the center of mass. So that's why this H you have to take as a half meter, because symmetric one. So I'm taking the center of mass to be situated at the middle point. So that will give you the height H. G as it is. So M is how much? The mass will be, see, 3, that means, you know, that will be 1 kg only, because 2 is to 1, the uniform one. Okay, uniform chain. So mass per unit length will be 1/3 into, oh sorry, 3/3 into 1, so it will be 1 kg only. Okay, so 1 kg. G as it is, G you have to take as 10, so I can write that as 10 here. So 10 G and H will be half meter, so you'll have -5. Okay, energy, initial, and this energy is the total energy conservation. So finally, suppose it has got certain kinetic energy K plus potential energy. So here the potential energy will be again at 3/2 meter. Okay, that means and see, this potential energy also will be negative because it is also taken below the reference level. So M will be total 3, G will be 10, and height will be 3 by 2. The center of mass. Okay, height of the center of mass from the reference level. Okay, so here I get the E final is equal to, so this is 5, this is 45, 339, so 45, K minus 45, right? So if I just equate this to K minus 45 is equal to minus 5, then what I get? K is equal to 45 minus 5, that is 40 joule. Okay, this will be the answer. Just let me tell you whether we have got the correct answer for this or not. Yes, this is correct answer. Okay, so this is 40 joule. So with this I'll stop it here for today. Next day we'll go for the set of questions from the 12th part of this paper. Okay, so thank you for your patience. Bye for today.